Okay, so let us start. Analysis of cables we were discussing, and I have given you a problem. So Onuj has mentioned today that you are facing some problem in solving the problem, right? So let me discuss that
Yes,
problem
sir,
first.
yes.
Hmm. So this is the problem. Can everyone see a footbridge of width, or let me copy it from here and then paste it in the Word document so it will be clear. So let's see. See, I think only the first part you are not able to understand. That's why you are facing problem. But other than that, you should be able to solve this problem very easily. See,
Yes, sir, the diagram part.
yeah, diagram part. Let me explain. Okay. A footbridge of width 3 meter and span 50 meter carried by two cables of uniform section having a central deep of 5 meter. Okay. So this is the part you will have to understand very clearly. So first thing, let me go back to the initial portion of the discussion we have done. So you see, this is actually a cable stayed bridge, right? So schematic diagram of suspension bridge, whatever we have seen in the earlier, and I have shared with you this diagram, right? So you see what is being said at the initial stage of the discussion. If you remember, see, a suspension bridges in suspension bridges, cables form an important structural component. So basically, whenever there is a suspension bridge, if you are suspending the deck of the bridge, okay, deck of the bridge, what is the deck of the bridge? So deck of the bridge is nothing but the platform over which the cars, people, vehicles are moving, isn't it? That is the deck of the bridge. Now you see, this deck of the bridge needs to be suspended by two cables on one side, one on each of the side, right? It cannot be suspended in one side, right? So you see, this is the front view of the bridge you are seeing, okay, or the side view of the bridge you are seeing. From one side, if you see, so you see the river is flowing. So if you are standing, let's say if you are standing here, somewhere here, you will be observing something like this. So you see, this is your bridge deck, this is your bridge deck, and you see this bridge deck is nothing but a rectangular kind of thing, right? So basically you see two cables, one cable is something like this, and this is one side of the bridge deck you are seeing. Exactly the similar replica, exactly the similar mirror image you will be seeing on the other side. So if you see, I'll just try to draw a diagram something like that. I don't know how much I'll be able to show it, because using this graphics and all. So you see how it is being. So you see, this is your let's say bridge deck, okay. So this bridge deck means basically the deck is something like this. So basically, if you observe, the bridge deck is something like this. Are you getting? This is your deck portion. This is your deck portion, or rather, I will just show it in this way. So you see, suppose this is the deck of the bridge. Are you getting? This is the deck of the bridge. Deck of the bridge means over this the vehicles are running, over this the vehicles are running. Now who is supporting this? Who is supporting this? See, on one side, on one corner, so if I take a cable something like this, let's say on this side, how do I draw it? Just a minute. So which shape should I take? This one will do. So see, on this side there is a cable, and this side there is a cable, and on the other side also there is a cable. From this side there is a cable, and this side there is a cable. So from this cable, or rather I am not able to draw it in a exact parabolic way. Let's say this is a cable something like this on this side. So there will be another one cable on the other side also, on the other side also. So you see, if you three dimensionally if you think, so how it will be, it will be something like this. So see, from this cable it is hanging something like this. So one to the one cable, oh sorry, to one cable the bridge is, deck is hanging something like this, and to the other cable, so this one if I little bit increase on this side and little bit of increase on this side, so you see on the other cable the deck is hanging something like this. Is it now clear? Is it now clear? क्या समझ में
Yes,
आया क्या?
sir.
हाँ?
Yes,
See,
sir. Yes,
this
sir.
is, this is actually the deck. See where, which one is the deck? Deck is this portion. See, this portion is the deck. This horizontal portion is the deck, right? So on one side there is a cable. This is one cable. Let's say this is another one cable. Think about these cables are parabolic. I've just drawn simple straight lines, but let's say these are parabolic cable. So on one side, sorry. So on one side this is a parabolic cable. So let me just for more clarification I'll just color it, so you will be understanding it better. So let's say these are cables. So line color, if I change it to red, let's say these are cables. So this is one cable, and another one cable is which one? This is one cable, and another one cable is this one. So another one cable, if I mark it something like this, format save, increase the width and then change the line color. So basically these two are the cables, okay? These two are the cables, right? Now these let's say these are the hangers. These are the hangers, one hanger, two hangers, so multiple hangers will be there, right? On the similar way, this deck on this side there will be another one cable, so hangers will be there. So you see there will be multiple hangers something like this. So these are the hangers of the bridge. So these are the hangers of the bridge, right? So on one side these hangers are coming something like this, and on the other side you see, on the other side also there will be hangers something like this. So if you just think from the three-dimensional view or three-dimensional perspective, then you will see, you will be getting a view something like this, isn't it? You will be getting some view something like this. So this is what is the problem given. In the problem it is given. So a footbridge of width 3 meter. So what is the width of the footbridge? So where is the footbridge? Actually see, this is your footbridge. So footbridge is nothing but this one, you see. I'll just show you this footbridge. So this is actually a footbridge. And so if I just format save, and very difficult to explain, that is what is the problem. So let's say this is your so you see this and this, these four consisting the deck of the bridge. So basically color is not changing, right? So see this one, just have patience, okay? Just let me color it, otherwise you will not understand, Is it okay? So see, this is your deck of the bridge. This color, whatever I have shown you just now, this is your deck of the bridge. Now you see, this is one cable, this is another one cable. So using the hangers, this deck is being hanged from these two cables. So a footbridge of width 3 meters. So width means from here to here the distance is 3 meter, and span 50 meters. So what is the span of the bridge? Span means from one end to other end, that is your span, 50 meter. Okay, now you see two cables of uniform section. So how many cables are there? One cable on one side of this bridge, other cable. So these red colored things are cable. This is one cable, this is another one cable. Where are they staying? They are on the both side of the bridge. One side of the bridge is this one. So deck, one side of the deck is being hanged to this portion of the cable, the other side of the deck is being hung from this portion of the cable. Through which it is being hanged? Through these hangers. So if you see the front view, or if you see the side view of this bridge, so you are going to see something like this basically. Okay, instead of this parabola, I have just drawn it something horizontal line, that's all. Okay, so you see in the problem what is being said, width of the bridge is 3 meters, span is 50 meters. So how much is the area of this deck? The area of the deck, you see, very simple to understand this one. So you see the area of the deck, just if you do not understand at any point, you tell me. Okay, so area of the deck, if you see, area of the deck is how much? Can anyone tell me? 3 meter multiplied by 5 meter, isn't it? Area of the deck, because 3 meter is the width and length of the deck will be 50 meter, because that is what is the span of the bridge. So basically area of the deck is 50 meter, 50 meter. So it is equal to 150 square meter. Any doubt up to this?
No, sir.
So once you know the area of the deck, now you see what is actually required. You need to know the value of W. See, in this problem, the value of W is not given. What is W? W is the UDL on the cable. So what is the value of W? That is not given. You see, in the problem it is not given. You see, the platform load, instead of that, the platform load is given as 5 kilonewton per meter square, right? So platform load is 5 kilonewton per meter squared. So you see the total load on the platform, how much will be the total load on the platform? So area of the deck is 150 square meter. So deck is basically the platform. So the total load from the platform will be how much? Equal to, see, this is square meter and this is kilonewton per meter square. So per meter square area, in per meter square area, the amount of load on the platform is given. So what you will do? Area multiplied by the load per meter square, or load per area, that you will have to multiply. So the total load on the platform will be 150 square meter, or I will write, instead of square meter I will write meter square, let's say. So it will be more clear, meter square, and then you will have to do what? Multiply it by how much? Tell me. 5
kilonewton
per meter squared. Now is it okay? Is it clear? So this is the total load. Now how much it will be? 5, 15, 75, right? 5, 15, 75, so 750, right? It will become 750.
Yes.
What will be the unit? 750 kilonewton. Okay. So 750 kilonewton. I'll write it in the next line. So is it okay? Up to this it is okay? So total load on the platform. So see, on this platform, the total load is 750 kilonewton. Is it clear now? Up to this point, is it clear?
Yes, sir.
Okay, very good. Now you tell me, if 750 kilonewton is the total load on the platform, each of the cable will be taking how much load? Because you see, whatever formula, whatever derivation we have done, you see we have considered that on each cable the UDL is acting, right? On one side of the cable, considering one side of the cable only, we have derived the formula. So there are two cables, right? On one side of the deck there is one cable, this one, other side of the deck there is one cable. So two cables will be equally sharing it. So each of the cable will be taking how much load? Tell me, how many cables? 250, two cables. So 750 by 2 kilonewton, so 375 kilonewton load. Now is it clear? So each of
Yes,
each of the cable will be taking 375 kilonewton load. Now is it clear? Now you tell me, if each of the cables, so the total load coming on the cable is 375 kilonewton. Have you understood? So what will be the UDL on the cable? UDL on the cable will be how much? Because as I have told you, if you remember, through this hanger, when the load from the bridge will be transferred to the cable, ideally the assumption is the load will be transformed in the form of uniformly distributed load, because the reason is the hangers, these hangers will be so closely spaced, they will be so closely spaced that for each of the amount of the load, you can assume that the load will be transferred just like a UDL. So if you consider this as UDL, then what will be the UDL on the cable? So UDL on the cable is nothing but your small w, and what will be the UDL on the cable? So total load is being carried by one cable is 375 kilonewton, and what is the length of the span? Total span length 50 meter, isn't it? So total span length I will divide it by 50. So this is your 50 meter, right? 50 meter. So basically, if you divide it, how much it will come? You can divide, or you can keep it something like that also. So it is going to be 375 divided by 50 kilonewton per meter. After that, you see your problem is simple.
7.5,
Huh? How much?
7.5, 7.5.
7.5 is it is coming? Okay, 7.5, 7.55, 7 is 35, 6, 7, 25, 5, 5 is 25, 10, 7.5 kilonewton per meter. Is it now clear? So you know now W, small w you know. So once you know small w, you can calculate your horizontal force H. So what will be your H? Tell me. It's from the formula you can get it. W L squared. W L squared. If you remember, W L
By
squared.
8 YC.
Bolo 8 divided by 8.
YC.
Exactly. 8 YC. Very good. So W L squared by 8 YC. Okay. So now you tell me, it's now very simple, you see. So W you know, so W is nothing but 7.5 multiplied by L squared. How much is the value of L? L you have no, you know, 50 into 50, isn't it? 50 into 50 divided by 8 into, what is the value of YC? It is given in the problem.
5.
YC, deep of the cable, right? So deep of the cable
Yes.
is 5. So 5. So you will get the value of H. So how much H value you will be getting? 5 8 is 40, 0 0. How much it is coming? 468 something is coming. 7.5 into 50 into 50. So if you do,
So 468.75.
okay, exactly. 468.75 unit will be kilonewton. So this is your horizontal force, right? Is it okay? Everyone now understood? Now what will be the vertical force V? What will be the vertical force V? VA is equal to VB will be equal to, because the cables are at the same level, so it will be WL by 2, right?
By 2.
WL by
Yes.
2. So what is your W in this case? W is nothing but your 7.5 into L is 50 divided by 2. That's going to be equal to how much? 7.5 into 50.
Sir, 187.5.
Okay, 187.5 is coming, 187.5
Yes, sir.
kilonewton. Is it clear now? Have you understood it? Okay.
Yes, sir.
So this is what is the horizontal force and vertical force you are getting in each cable, isn't it? So what will be the tension component? So you remember what is T max we have calculated. So T max is nothing but, so if you remember, T max is what? T max, tension in
Root
the cable is equal to square root SQRT square root of V
H squared
squared
plus B squared.
plus H squared, right? That's what, right? So V squared plus H squared. So V square plus H square. So if you calculate it, you are going to get what is the value of this one. So it's going to be T max equal to root over of V square plus H squared. So SQRT square root of what is your V squared? Sorry, H square. V squared is how much? 187. So 187.5 squared, right? So this is going to be 187.5 squared, and then plus it will be 468.75, then squared.
540.
Just a minute, I am going little bit slow. Okay, now 187 square, 187.5. Have you calculated? 500
Yes.
or 504 it is coming?
4.67, sir.
504.67 or 68 it will come, right? This much. Is it clear? So have you understood? Is it clear?
Yes.
Yes, sir.
So see the problem is simple, right? Problem is simple. Only thing is the diagram you will have to understand. Okay. So now physically understand how the load is getting transferred from the bridge deck to the cable. So from the bridge deck, see on the area of the bridge deck load is there. So cars are moving, people are running, vehicles are moving over it. So at per kilonewton per meter square run. So per kilonewton per per meter square, how much load is there on the deck, that is given. So you first calculate the area of the deck, get the total load, divide the total load in two cables, then from the two cables the total load you convert it to UDL, and after that the problem is simple, right? So it's nothing complex. It's already we have explained this problem earlier also. And the second part of the problem, will you be able to solve? Find the necessary section area required if the allowable stress is 120 Newton per millimeter square. Below. Second part of the problem. Anyone? No idea?
No, sir.
Think about it. Think about it. It's the simple problem of strength of materials. If you see, the second part is simple strength of material. Initial thing whatever we have discussed. Ekdam strength of material chapter ka first things whatever we have discussed. That is there. Nothing else. Buddhadev, can you tell? So see, tension is coming onto the cable, right? So tension T is coming onto the cable, right? So how the tension will be taken by the cable? So because of the tension, there will be internal stresses getting developed inside the cable, right? And you see the allowable stress value is given, and you require to have a particular cross sectional area of the cable, right? Then only the tension can be taken. So I can write it something like this, that T max equal to T max, whatever is the maximum tension in the cable, that is equal to how much? The allowable stress in the cable multiplied by the area of cross section of the cable, isn't it? Can I write this? Simple strength of materials, it's nothing else. It's just that strength of materials thing you are so it's simple strength of materials you are just applying, okay? So allowable stress in the cable multiplied by area of cross section of the cable. That's what you will have to do. Very simple. Correct or not? Okay? So if you think that the allowable stress in the cable is given now, allowable stress in the cable is given in the problem, you see. What is the allowable stress? Allowable stress given is 120 Newton per millimeter square, isn't it? So 120 Newton per millimeter square is the allowable stress in the cable. So you just put the value over there. So very simple. So T max is nothing but your 120. You should be a little bit cautious about your unit, okay? So you see this is given in Newton per mm squared, okay? So this is given in Newton per millimeter squared. So once you have this Newton per millimeter squared, so you see your area of cross section also will be coming in millimeter squared only, okay? So what you will have to change? Multiplied by area of cross section. So what will be your T max? What is your T max? T max is nothing but your 504.68. This is in kilo Newton, right? So instead of that I should change it to Newton, because you see from on the other side the unit is Newton per millimeter square. So if you do it, then you will directly get area of cross section value. So what will be your area of cross section? Sorry. So area of cross section is going to be equal to 504.68 multiplied by 1000 divided by 120. Okay? Is it clear? Or do you have still doubt?
Yes, sir, clear.
So please calculate the value. Please calculate the value. 504.68 into 1000 by 120. So please get the value.
4205.66, sir.
4205.66, right? 205.66 millimeter squared, right? It will be millimeter squared. So please be very careful about your unit. Unit system is very important, okay? Because you see here it is Newton per millimeter squared, and here it is kilonewton, okay? So kilonewton into 1000, so Newton, and Newton per millimeter square, you divide it, area of cross section. See, it's you will have to apply your strength of material concept over here. So a simple cable, you see, so cable is under tension. So while it is under tension, when you are pulling it, then how it will be resisting the pull force? It will be resisting the pulling force using its internal stress, right? Whatever stress will be getting generated, right? So a tensile stress will be getting generated inside the cable. So the allowable tensile stress inside the cable is given. So you multiply it with the cross section, and you are going to get the value of the total tensile force. From that you should be able to get the area of cross section of the cable. It's a good problem actually. So it's little different. Different means it's kind of a practical kind of problem you are getting over here. So now can I expect that you will be able to solve this problem your own?
Yes, sir.
Okay. If you have any doubt, you can ask now, because otherwise I will go to another one part, because already it's 3:40. Is it okay?
Yes, sir.
Okay. So I'll just discuss another one part today, and we'll conclude the discussion on cables today itself. Okay. From next week onwards, or so for in this week only, I think on Saturday I have another one class, right? On Saturday's class we will start discussing about analysis of indeterminate structure, indeterminate beams and other things. Okay, so that discussion will start. So I'll try to conclude, I'll finish the discussion on cable today. So you see, whatever we have discussed till now, you see on that, see the discussion till now we have made, where we have said the supports of these two cables, that means the support on which the cables are kept, they are at the same level. That means, you see, if I go to this figure, that means the on either on the roller support or on the saddle support, either on the pulley support or on the saddle on roller, whatever may be the case, the cable in this case, whatever analysis we have done, you see the supports are at the same level. The level of this portion and the level of this portion is at the same level, right? These two are at the same level. Okay, so the main cable when attached to these supports are at the same level. Okay, and see these anchor cables or the backstays are going behind and it is pulling it and it is just placing it tight on the ground. Okay, so once you see this main cable is being supported at the same level, we have developed formulation and we have analyzed it. Now there may be cases, you see, there may be cases where you may be getting valleys, something like that, where one side is too low and other side is too high. So in that case you may expect a deck, okay, where the one side of the support will be at lower level than the other side. Okay, just if you see the diagram, it will be clear to you. So see when the supports are at same level, you see you are going to get a diagram something like that. But if the supports are at different level, just I'll show you with the diagram in the handout. It is given just at the end of the handout, you will notice. So you see this kind of diagram you are going to get. You see one support, this support A is over here and support B is over here, and you see a UDL is being supported on the bridge. So you see deck is somewhere here, deck is somewhere over here. On this deck is being supported through the hangers, and hangers are being attached to this cable, right? Hangers are being attached to this cable. However, you see one side of the support is at lower level, other side of the support is at the higher level. Where it will happen? You see, it's a, let's say you have a valley. On one side it's a deep valley and one side there is a hill, let's say. So what you may expect? On one side you may be expecting a pier at the lower level, and on the other side the pier will be at the higher level. Okay, so in such case, if you want to analyze the cable, then how will you proceed? So that is the question. Okay, so it is also very simple. I will not get into complete mathematics of it, but it is very simple to do. So 2-3 things you should remember over here. First thing you should remember, when the cable will be supported at two different levels, you see from this support level, from this support, that is the lower support level, from the lower support level, if I draw a horizontal line something like this, okay, then if you observe, I have written a term called YC over here. Okay, so this is actually the dip for this portion of the cable. That means up to what? Up to this length L1 of the span. So the total span, if you see, total span of the cable is L1 plus L2. Okay, so total span of the bridge deck is basically L1 plus L2. Now you see there is a separate parabola you are getting from here to here, and on the other hand you see there is another one parabola you are getting from here to here, or rather I should show it here to here. And you see, this support, when you consider, if I draw a horizontal line from here, you see the dip of the cable will be from that horizontal line to this point. Okay, so how much it will be? Let's say from this horizontal line, that means from this support to this point, if the distance is yc, and from this horizontal line to this support, that means the difference of the height of the support. You see, what is this d? D is basically the difference of the height of this support. So the top level of this support and the top level of this support are at a differing level of this distance d. Isn't it, or height d? So the upper support, from the upper support, you see the dip of the cable up to this C will be d plus this yc, and for the lowermost support, or this portion of the cable, the dip will be small yc. Okay. Now considering this, one thing you must remember in case of the cable, you see, in this case you are not going to get your VA is equal to VB. See, in the previous case, when the supports are at the same level, what are the value of VA and VB you have got? You see, you have got VA is equal to VB is equal to V is equal to WL by 2, right? However, in this case, when the supports are at different levels, you are not going to get the value of the vertical forces at the two different supports which are located at different levels. They will be different. Basically, they will be different. Okay. Now, this can be very easily derived if you consider different equilibriums about this point C. That means if you take moment about C for this portion of the cable, if you take moment about C for this portion of the cable, if you take moment about B, then you should be able to solve the equations. So you see, what are the unknowns you have in this cable? So you see, you are going to have unknown equal to VA, you are going to have unknown equal to VB, because VA and VB both are unknown. Why? Because VA is not going to be equal to VB. On the other hand, if you observe, your HA will be obviously equal to be will be always equal to HB, because you see the tension component, the horizontal component of forces must equate each other, because these are nothing but the hinge supports, right? These are kind of hinge support. So this horizontal component, for equilibrium of this total system, the horizontal force component at the support A must be equal to the horizontal support reaction component at support B. So if you consider this, then, and if you think that how many unknown components now you have three unknowns. You see, you have unknown VA, you have unknown VB, and you have unknown HA and HB who are which are equal basically. So HA equal to HB equal to H. So you have three unknown components, right? So if you consider these three unknown components, and if you take the moment of all the forces about C, as I have earlier told you that at any point in the cable, on the cable, if you take moment about all the forces, the moment must be equal to 0. Why it will be equal to 0? Because the moment the cable can only take tension, it cannot take any kind of moment. Okay, so sum of all the moments should be equal to 0. So if you take moment about C for this portion, if you take moment about C for the other portion of the cable, and if you take moment about either B or either A, then you are going to get three equations, right? So those three equations will be comprising of three things. One is your VA, one will be VB, and another one will be H. Okay. So once you have the three equation, you should be able to solve the equation, and you should be able to find out the three unknowns. But you need not to go to the details of that solution. Rather, for solving this kind of problem, you should remember this formula very well. So if you see, very simple to remember, if you solve those three equations I am telling, if you solve those three equations, you are going to get this kind of equation finally. So your HA should be equal to HB, and the value of HA, see, if you remember, for the supports at the equal level, when the supports are at the equal level, what is the formula for horizontal force? Just few minutes back we have solved the problem. What is the formula you say? Tell me. W into, bola, what is the formula you said? Bola, bola. Bolo, when the supports are at equal level, what is the formula you have said for H? What is the horizontal force?
So WL square by 8.
WL squared by 8yc. So exactly the same phenomena we will be using over here. So you see, considering this portion of the cable, you see, only thing you should be very careful about here while writing this formula. You see, this is the half portion of the cable, right? This is half portion of the cable. So this is half portion of the parabola, okay? So L1, instead of this L1, we will write here horizontal force. When we will be writing HA equal to W into L square. Instead of L square, we will be writing 2L1. 2L1 whole squared by 8yc. And what will be my HB? HB I will be writing W into 2L squared. This from here to here it is L2. So if I take a complete round of this parabola, so what will be the horizontal force? The horizontal force is going to be W into 2L squared by 8 into YC plus D. So YC, you see, for this much portion of the cable, the deep is how much? YC. For this portion of the cable, how much is the deep? Deep is YC plus D. So same formula, you see, same formula we are using, just with some modification, because you see, these values you will be getting if you solve those three equations I have told you. That is, if you take moment about C, if you take moment about C for one portion of the cable, if you take moment about C for the other portion of the cable, and if you take moment about either B or either A, then you are going to get three equations. If you solve those three equations, you are going to get the final values for HA and HB. But if you want to do that, you will be landing up with bigger solutions. But when you will be solving the problem, you must remember from some analogy, and using the analogy you can easily write that for this portion of the cable. So if you think that this parabola is getting complete up to this level, so how much will be the horizontal force? Horizontal force will be W into 2L1 square. From here to here it is L1, and from here to here it will be L1. So W into 2L1 square by 8yc, and HB will be W into 2L2 square by 8yc plus D. Okay. Now you see, what is the final thing we will write? We know that HA must be equal to HB. I have explained you why it will be. And then when HA is equal to HB, I can write W into 2L1 squared by 8yc equal to W into 2L2 squared divided by 8 into yc plus D. So you see what I can write, W into 4L1 squared, W into 4L2 squared, here it is 8H1 and here it is 8H2. So what is H2? H1 in this case we have written H1 is nothing but YC, and YC plus D we are writing it as H2. So you see, I can write it something like this: L1 squared by L2 squared equal to H1 by H2 equal to YC by YC plus D. What is H2? H2 is nothing but YC plus D. Okay. So from this equation you see what you are getting. Actually you are getting a relation between this L1 and this L2. Okay. So once you get the relation between this L1 and L2, you should be very easily able to find out the value of the reaction components Va and Vb. Okay. So what will be your Va? So Va is nothing but, in this case you see Va is going to be Va into L. Why? Va into L. Now you see Va. So take moment about B. So if you take moment about B, what will be this? Va into L1 plus L2, which is nothing but L. And then HA. This HA is going to create moment about this point. So HA into how much? D plus YC, right? So HA into D plus YC. So you see that's what is being written. HA into D minus, sorry, not D plus YC. HA is being at the horizontal level of this. So two support level difference is D. So HA into this much distance D. This is the lever arm. Okay. And this W is going to create moment about this point. So how much it will be? W into L by 2. So you see that's what is being written over here. So Va into L plus HA into D minus WL squared by 2 is equal to 0. So you see the value of Va is going to be equal to WL minus 2 minus H into D upon L. On the other hand, if you take moment about A, you are going to get the value of Vb, and this Vb is going to be equal to WL by 2 plus H into D by L. You see the difference. You see the difference now. So when the supports are at same level, at that time you see what you have got. You have got Va is equal to Vb is equal to WL by 2, right? But when the supports are at different level, you observe the lower support, the reaction at the lower support, you should be very, very cautious about it. Okay, don't get confused. See the lower support, at the lower support, you see the lower support, the reaction will be lesser. You see at the lower support, the reaction will be lesser. So it will be how much? WL by 2 minus of H into D upon L. What is D? D is the difference between the height of the support. And what is L? L is the total span of the bridge. On the other hand, if you see, if you see the Vb, that means Vb is the reaction force, vertical reaction force at the higher level of the support. And at the higher level of the support, if you see, the reaction force Vb is going to be equal to WL by 2 plus H into D upon L. Okay. So minus and plus, where it will be minus. So you see WL by 2 to this WL by 2 term, only a plus and minus term is either getting H into D by L, this term is either getting added or subtracted. So where you will be subtracting? At the lower support level you will be subtracting, at the higher support level you will be adding. Okay. After that the problem will remain same. So if you want to find out the maximum TA, if you want to find out TB, then you can easily find it out. And you notice over here the value of the tension at the cable at the support level will be different. You see at the level at A it will be root over of Va square plus H square. At TB it will be Vb square plus Hb square. Is it clear? So Ha and Hb are equal, however Va and Vb are different. So Ta will not be equal to Tb in this case. Is it clear to everyone? Have you understood?
Yes, sir.
Okay. So considering this, I have taken one problem from C.S. Reddy's book, but I don't have time today. So it's a simple problem. So see, this is the problem. So what I will do today, it will not be possible. Okay. So what I will do next class, maybe I will first discuss this problem, then we will start with this, what is called indeterminate structure analysis. Okay. Okay, then. So do you have any doubt up to this point? So all of you please submit this assignment. Okay. the problem whatever I have discussed. I have not closed the assignment yet. Okay, which one? This one, structure analysis 1 C1, 21st November 2020. So you please submit this assignment. Okay, okay, let me take the attendance and then we'll stop. Okay. See, now onwards we will monitor the attendance. Okay, so please attend the classes regularly. Okay, so thank you very much. Saturday we'll meet again. Okay,
Thank you, sir.
Thank you, sir.
thank you.
Thank you, sir.